In this lesson, we're going to continue our study of thermochemistry. Today we'll be looking at thermochemical equations, combustion reactions that produce heat and light. Okay, so today we begin looking at calculations that involve heat of combustion. Now, heat of combustion is pretty much what it says. It's the amount of heat given away when you burn something. Okay? The kind of heat of combustion reactions or calculations we do in here assume some basic things. For example, water has a huge heat capacity. We've talked about that already. So if I am burning something that has water in it, the water is absorbing heat while also the thing we're burning is giving away heat. Okay, so you have to know about the balance there. For our calculations, we're going to simplify this down almost to the point of absurdity. We've talked about that before. For high school chemistry, we start with really simple stuff and eliminate all the things that can interfere with what we're looking at. And we're doing it, keeping it very, very simple, okay? So what we're going to look at is how you go about representing heat of combustion, how you handle chemical equations with heat of combustion, and then how we do the math. All right, so it's a dimensional analysis problem, and it's a little bit different than the dimensional analysis problems we've been doing so far. Now, for the record, when I teach this in the spring semester, this unit comes at the very end of everything, so a lot of the things I'm going to explain here have already been explained in previous units, but for you guys, I'm explaining it as if you've never seen some of these things before, okay? Like balancing equations, I know you've done that in physical science, but we've not done it in here. Okay, so let's move on here. So, if we're going to deal with heat of combustion, we've got to understand the difference between what's happening in the system and what's happening in the surroundings. Now, 2 days ago, we talked about that, system and surroundings. We repeated that yesterday. What is the system and the surroundings? So, if something is exothermic, it's giving heat away to the surroundings, which means that the system itself is losing energy. So delta H is losing energy. Okay, so let's remind ourselves about system and surroundings, okay? So the system is the place where our chemical reaction is actually taking place. It's the chemicals themselves, okay? Not the stuff that's around it, not the air or the water that surrounds it. Okay, the example I gave yesterday was if we had vinegar and baking soda reacting together. Vinegar is mostly water. It's 95% water. Only the acetic acid is reacting with the baking soda, which is sodium bicarbonate. And so that water is not even part of the system. Vinegar is mostly water, but the water part of the vinegar is not even in the system. It's part of the surroundings. It's only the chemicals themselves that are involved in the reaction that are the system, okay? So you've got the system, and everything around the system makes up the surroundings. And the surroundings go to the uttermost parts of the universe. Okay, we're talking about if we were doing some reaction on a lab bench, it'd be the water that surrounds the chemicals, it'd be the container it's in, it'd be the lab bench, it's the room, the building, the school, everything, all the way out to as far as you can imagine, even beyond what you can imagine, probably. Okay, but all together, system and surroundings make up the universe. All right. When we're talking about combustion reactions, then you have to keep in mind whether or not you are dealing with something that's happening in the system or something that's dealing with the surroundings. Delta H, the change in energy, at least that's how we look at it in high school chemistry. It really is a bit more complex than that, but for high school chemistry, we're going to simplify that down, simplified to the point of absurdity, simplify it down to saying it's just the energy stored in something. And since it's changing that, it's how much energy is being changed in the system among the chemicals doing the reacting. Okay? Going from reactants to products, how much that stored energy changes. So an exothermic reaction gives away energy. That giving away part is the surroundings. It's where you and I are. In the system, then, an exothermic reaction loses energy. So if we're burning something, that is always going to be exothermic. You can imagine it is because it gives away heat, right? In fact, here's the definition of combustion. Actually, there's a couple of definitions. We're going to stick with the very simple, again, simple to the point of absurdity, the simplest type of combustion, okay? Combustion really is any reaction that involves oxygen that produces light and heat. Any reaction that involves oxygen that produces light and heat. For us, the only combustion reactions you're going to be dealing with are even simpler than that. Okay? If I were to burn hydrogen gas, well, that reacts with oxygen in the air, and all combustion is reacting with oxygen in the air, pretty much. Well, for us it is anyway. And we produce water as a product, okay? But we're not even going to deal with that kind of reaction. I'm going to use it as an example, maybe, but we're not going to be using that for the actual calculations we do in here. For us, all our combustion reactions will have a hydrocarbon fuel. And that hydrocarbon fuel will react with oxygen, and the products are always the same, okay? For us, the combustion reactions we're going to be dealing with will have a hydrocarbon fuel. That hydrocarbon fuel will react with oxygen, and the products will always be the same. They will always be carbon dioxide and water. Okay? The carbon dioxide is a gas, and because of the heat of combustion, the water will also be a gas. It'll be steam. Okay? So, let's go back to delta H. For us, all of our combustion reactions are going to be, they're all exothermic, so inside the system we're losing energy. Okay? It's always going to be a negative number. Let's give you a simple combustion reaction here to start with and kind of explain what we're talking about here. All right? So let's look at the combustion of methane. Methane is a very simple hydrocarbon gas. Now, the word hydrocarbon kind of tells you what it is. It contains two elements. What do you think those two elements are? Water. Hydrocarbon, hydrogen, and carbon. Simpler than just water. Hydro, I know, is a prefix. Sometimes it means water. But this is hydrogen and carbon. That's it. Okay. Methane is the simplest of all the hydrocarbons, and it's CH4. It's a gas. And in the chemistry lab, when we use the gas that's coming out of the pipes on the desk here, the jets on the desk, that's mostly methane. It's kind of a mixture of gases, but it's mostly methane. Okay?
Is that a 5 for an S?
That's a G for a gas. Okay? All right. And so it's going to always react with oxygen. Every time we do these kind of combustion reactions, we're always reacting with oxygen and oxygen in the air. So what physical state does the oxygen in the air have? It's a gas. Okay? All right. And so it's always going to produce the same two products. What are the two products? No, I said a while ago what they were. Carbon dioxide and water. Always going to produce these products. Now we've already mentioned that the left side of the arrow here in a chemical equation, those are reactants, and the right side of the arrow in a chemical equation are products. And the products here are always going to be carbon dioxide and water. And what physical state is the water going to be in? Yeah, that's right. I said a gas a while ago, so that's what it is. All right. Now, this is not a balanced equation, and I know that you guys learned to balance equations by inspection when you were in physical science. So this is not balanced, okay? You learned to balance by inspection when you were in 9th grade. What do I need to do to this equation to balance this equation? Where's the 2 going to go? To the water. Okay, so I need to put a 2 in front of the water. Okay, you cannot, once the formulas are balanced, you can't plug numbers in there. You have to put them in front. Okay, that's a coefficient. You knew that was a coefficient from algebra, right? No. You should know that from algebra. I'm going to contact your algebra teachers. Okay. Now, is it balanced now? How many oxygens do I have on the right? 2 here, because of this 2. Now I have 2 here. That's a total of 4 oxygens on the right. So I need a 2 in front of this to balance the equation. All right? Later in the year, we will learn a new process of balancing equations, but for right now, that's fine. What we're doing is fine. Okay? It should be good for this. I might even explain it in this unit here shortly about how to do that. So this is now balanced, and what you don't know yet is that when you burn this, if I burn 1 mole of this, now mole is the SI unit for the amount of substance. The mole is the SI unit for the amount of substance. The mole is the SI unit for the amount of substance. If I burn 1 mole of this stuff, it will produce 890 kilojoules of energy, heat energy, mostly heat energy. It'll be some light. Okay? If I burn 1 mole of this stuff, then it's going to produce 890 kilojoules of energy. Now, I can handle that in one of 2 ways. I can include the heat energy in the equation. All right? If I include the heat energy in the equation, it's representing the energy that's a product, which means it's coming out to us. Okay? So that's not in the system, that's in the surroundings. That's the heat product that's coming to the surroundings. So, if I include energy in the equation, it would look like this. Okay? If it's in the equation, this is what's happening in the surroundings, not in the system. Okay? System, surroundings, energy moves from one place to the other, but you can't get rid of energy. One of the thermodynamic laws of the universe. Okay? Huh? I still don't understand the question.
She sneezed.
Oh, okay, gotcha. Oh, you just said bless you. Okay, I got it. All right, so let's don't include E in the equation. Let's include the energy in a delta H term. Okay? Now, this is not going to be, we're not going to have the energy in the equation now. We're going to be representing, since delta H is what's happening in the system, you have to know that. If I include the energy as a delta H term, you have to know that's happening in the system and not the surroundings. This is the surroundings. This is the energy that's being delivered to the surroundings. Okay? So here's what the equation is going to look like if we're going to show energy as a delta H term. So basically I've written them as 2 separate things. I wrote the equation here, and I'm saying for this equation, we're taking 890 kilojoules per mole out of the system. Now, when you look at a chemical equation like this, we usually think about this as being 1 molecule of methane, 2 molecules of oxygen, 1 molecule of CO2, and 2 molecules of H2O. Okay? But to a chemist, you look at this equation, you say that's 1 mole of methane. And that's 2 moles of methane. 1 mole of carbon dioxide, and 2 moles of H2O. So I need to define for you what a mole is. Okay? Later in the semester, we'll learn about some other things that the mole is equal to, but the The mole itself, 1 mole of anything, and they have to be particles of some kind, separate, distinct things, okay, is equal to 6.022 times 10 to the 23rd of those things, okay? And again, that's the particles we're talking about here. All right? That's a pretty big number, right? That's 6022 and 20 zeros if you were writing it in other than scientific notation. That's a lot of molecules. You with me? Just as an aside, each year on October 23rd, 1023, each year on October 23rd, 1023, October's a 10 month, 23rd day, we celebrate Mole Day. Mole Day begins at 6:02 a.m. and ends at 6:02 p.m. It's only a 12-hour celebration instead of a 24-hour celebration.
So do we wait, what was that? What was that decade?
1023.
So if we're in school, can we not do anything in here that day?
No, we will do something. We'll be celebrating Mole Day. Maybe. I don't know yet. Yes. What? 890. Oh, this? That's the amount of energy that you get out of burning 1 mole of methane. So the system is losing that energy, and the energy is being delivered to the surroundings. So what's happening here in delta H, this is in the system. So the system is losing 890 kilojoules for every mole of methane we burn. No, you don't have to memorize that. No, I'm gonna give you a reference to look at if you need to find those kind of things. Okay, something like this. All right, I'm just explaining it right now. Okay, just explaining it right now. All right. Now, if I burn 3 moles of methane, I want to find out how much heat will be produced. Now that word produced implies products, this side of the equation here. And when we include the energy in the equation, if it's an exothermic reaction, that's a positive number because that's telling you what's happening to the surroundings. Okay? All right. So let's write out a dimensional analysis problem for this. Okay? The starting amount is 3 moles of methane. Now, 3 moles is a counting number. All right? We don't use that 3 when it's written like this anyway as a for significant digits. All right? It represents 6.02 times 10 to the 23rd molecules. Now, if I had a fraction there, then I'd be saying it was some kind of calculated number. But if I just say 3 moles, whole numbers, the implication is that that's not considered what we use for significant digits. Technically, it's infinitely significant. That's why we don't use it. Okay? So what do you do with starting amounts in dimensional analysis? What do you do with the starting amounts when you're doing dimensional analysis? Well, you usually need an equality statement. That's true. What do you do with it when you put it in the problem? Put it over 1. Let's talk about equality statements, okay? Because up to now, we said that we have to have an equality statement anytime we do a conversion. If we have 2 things that are equal, okay? In this case, the 2 things we're going to look at are not actually equal. All right? It's a little bit different. Now we've got into things that are conversion factors, but are not also conversion units. Okay? We don't need an equality statement because we have a balanced equation for this relationship we need. Okay? We don't need an equality statement if the relationship we need is found in a balanced equation, and it is. Okay? In this balanced equation, where the energy is included in the equation, there's 1 mole of methane represented here, and 890 kilojoules represented here. So all we have to do is take the balanced equation. If we don't have a balanced equation with the factors we need, then you have to have an equality statement. Okay? But if the factors you need for the conversion are found in a balanced equation, then you have to have a balanced equation. And you have to know which one to use where. Okay, for this conversion, going from moles to kilojoules of energy, we found what we need in the balanced equation. Okay? So, in this equation then, we have 1 mole of methane represented here. 1 mole of methane. And we also have 890 kilojoules represented here. 890 kilojoules of energy. Okay? And we do the math. You have a calculator? Everybody should have a calculator. Try it out. Let's find out what we get. Alright, so we're going to take 3 and multiply that by 890. Well, if I can get my calculator to work. 3, come on now. Oh, I'll do it this way if I have to. Times 890. There we go. And we get 2,670. 2,670. And looking back on the paper we're working with here, we're going to get rid of the moles and the unit and the species. The species is the chemical here. That's the methane. We're going to get rid of that too, leaving ourselves with kilojoules. Okay, we said that the 3, the counting number, is not used for figuring out significant digits. So we got how many significant digits here? 2. I heard some 3s. Those of you who said 3, find somebody who said 2 and ask them to explain it to you.
Because a 0 is not a significant number?
Well, why is it not a significant number? Why is that 0 not significant?
Between 2 numbers. It doesn't follow the rules.
Okay, it has to follow one of the 2 formal rules. So does it follow both a decimal place and a non-zero digit?
No.
No. Is it between 2 significant digits? No. So that 0 is not significant. So we only have 2 significant digits. Therefore, we need 2 significant digits in our final answer because this is the only number we're using here. So 1, 2, underline everything else. Move our decimal place from the implied location it exists in, where it exists now, here, 1, 2, 3 places. And we get 2.7, good, times 10 to the 3rd power kilojoules. Does that make sense to everybody? All right, now that shouldn't be too hard. All right, we're taking something you already know, how to balance chemical equations by inspection. We're just adding in the concept of the heat energy. If you're including it in the equation, it looks like this. If you're including it as a separate thing, delta H, what's happening in the system here, the signs change. It's opposite signs, okay? And we're just including it in the equation, and we're using this equation to figure out the relationship among moles. So for every mole of this, we're making 890 kilojoules of energy. And if you look here, the way that I wrote it, there's a mole of methane in the equation, and it says we're losing in the system 890 kilojoules for every mole. Does that make sense? All right, then. I'm going to let you guys do one now. Well, you can only pass the class if you don't pass on the practice work. Okay, so here's the problem. Write it down. Write down the problem. And then I'll show you the heated combustion table that you can use to figure out how much heat energy is involved. You can work with a neighbor. And then while you're working on that, I'll go and print this heated combustion table for you. What is propane? I'm going to show you that as soon as you write the problem down. Have you written the problem down yet? Okay. Has anybody not yet written down the problem? Well, let's get her done. That's right. Yeah. I wonder if he has copyrighted that phrase. Cable guy, what's his name? Larry the cable guy. Because, he used that get her done. Okay. And a few years ago, it was like everybody said it all the time, and it was really annoying. But it's a little less, popular now. Anyway, but I wonder, since he uses it so much in his comedy routine, if he's copyrighted that material. And I can't say get her done without paying him for it. I'm just wondering. All right. Hopefully not. It's kind of in the common lexicon. And this is an educational video, so I should be okay. I hope. But if Larry the Cable Guy's watching this, just let me know. We'll talk about it. Anyway. Everybody good? You ready for the table now? All right, here's the table with the information you need. All right? So you need to find the propane that's listed on here, figure everything out, and solve the problem. All right, so we're going to have a guest teacher, a student, going to try to solve this problem for us. See how he does? Now look, listen up, listen up, listen up. Even though
I'm wrong.
Even though he might be wrong,
I will.
you have a part in this.
You don't.
If he's wrong, it's your job to help him out.
Yeah.
Okay?
Trey, that's you.
In this class, this is a collaborative
Mr.
effort.
Octavian, can you please be quiet?
Okay? Let's go. Come on. Don't waste time.
I'm not wasting time. I'm just taking my time.
Don't take your time.
Right. So, I think it's 25.
Let's see how he does.
There's 2.
Well, this isn't going to be slow like that, is it? All right.
So that's 25.37.
Just do it. They're going to help you out.
No, y'all should be getting around.
Moles. What's the propane? What is it? Okay. Alright.
You forgot your species.
I'm going back.
We don't know what kind of species.
You do not backtrack.
It's not even 220.
Oh, you
Where'd
can
get that?
backtrack.
No backtrack.
It's 2021. What are you doing?
What do you mean it's 2021?
Where'd you get the 2?
Yeah.
I did the wrong one.
Yeah.
That's
Trey,
a
what is it?
negative.
Trey, can I get some?
It's positive.
Is the propane symbol P?
Look on the sheet that I gave you.
It's over there.
The formula's there.
You're right, dude.
You're right.
Oh, I left it up.
Well, let me put it on the screen so people can see it. There's propane. So where's the chemical symbol for it?
No, not that one.
That's the chemical symbol for propane.
So why is there like that one?
That one. No, just that one right there. You know what that is, don't you?
Yeah.
That's oxygen.
Yeah.
What's that?
Carbon dioxide.
And what's that?
H2O.
So that one's the only one that could be propane.
Oh,
right?
makes
Okay.
sense. Okay, I got you.
All right.
Wait, keep it here. Trying to find it again. H.
4.
H.
Hey.
Like the number 8.
You see it? Right there.
Oh, yeah, it is 8.
Alright. So now you multiply.
On the bottom. No.
To me? Oh yeah, I forgot. Okay, yeah, give me time.
No, you forgot the C3H8. You forgot the
Yeah, he did forget that too. That's true. But you're helping him out.
You're forgetting stuff.
Can you have kilojoules?
Oh, yeah. True, true.
And the C3H8. Yeah, there you go.
What was the answer? I didn't multiply it.
Not yet.
Why don't you volunteer for this if you haven't done the math yet?
I was making sure to do it right. Now I know. Now I know.
Alright, we're good.
No, I'm probably gonna be right. Oh, did it wrong.
Wait, why did we change it to a positive?
I did.
So
So you take away the mole.
Take what?
It was negative 2 to
Yeah, so why is it a positive now?
I thought it was positive.
No, it was
No,
negative.
But when it's in the equation, it becomes positive.
And why is that?
Because that's how it goes.
No, it's not just how it goes. Why is that?
Yes, why is that?
You don't know?
Me either.
For what?
I only said it about 3 times.
I wasn't listening.
You weren't listening.
now. What'd you say?
Why does it turn negative?
Why does it go from negative to positive?
Yeah.
When it's written separately, where's the sheet? Here we go. When it's written separately as a delta H, that's what's happening in the system. When you put it in the equation, it's part of the
System.
surroundings. And if it's in the surroundings, if the system is losing energy, the surroundings are gaining energy. That's why it's positive.
Okay, so I thought.
Come on, people, listen.
I was listening. I just forgot. So you take away the mole. What?
You take away all of that. The
Yeah,
one,
you got.
three, and
Do you got? I was getting there. I take away the propane. And my answer on my calculator is 5, 6.
56,000.
Oh,
0.4. That's the capital. Honestly.
You gotta add your 1 so you won't get confused. Then.
Well, you don't have to put it over 1, but that's okay. It's not wrong because by putting it over 1, it's not wrong, but you don't have to put it over 1.
then you're cutting the round off.
You did something wrong.
Where?
You forgot
Macaroni
everywhere.
cake.
You didn't put the equal.
No, he's got an equal
I
sign.
got.
You forgot to
Alright,
sign two.
alright.
Put it in scientific.
I'm getting there.
Y'all are making him nervous.
But it's with the drama.
I know. I don't know what to do anymore. Alright, so go from the dot. 1, 2, 3, 4. So you get 5. Oh yeah, I got an underline. So you got. That's 3, right?
Three significant digits because that 0 is not significant.
Can you tell me why it's not significant?
Okay, the 0 is not significant because to be significant, this 0 has to meet one of the 2 formal rules.
Does it have to be
One of the
in middle?
rules says the 0 has to follow both a decimal place and a non-zero digit. This 0 follows a non-zero digit, but it doesn't follow a decimal place. The other rule says that zeros are significant when they are between 2 significant digits, and that's clearly not between 2 significant digits. So that 0 is not significant. Therefore, this number has 3 significant digits. This one has 4. You want your final answer to have the same number of digits as the measured or calculated number with the least digits.
Yes, sir. So you underline.
Yes.
Yes. Yes. Alright, there you go. 5 point. Is it 6-3?
Yes.
10 to the 4th. Alright, so, and then
Oh, you got the K right this time. Good job. No, it's not equals. It's not equals. Arrow. Arrow to show you rounding off. Really, Really, you only need the arrow between this number and that number. There really should be an equal sign here, so that is equal to that. Okay, we'll get that. Hopefully better. All right? We'll get
Sir.
All right, now. Yeah, he did a good job. He did a good job.
That's
Look,
lowercase k.
so in the future, if somebody comes up here, it's not their responsibility to do the math. It's yours in the class to do the math and help him with the math, okay?
That's right.
What the person up here has to do is simply set it up, okay? Got it? Now, of course, your job is to also help them by giving them some guidance, and like you did. Okay, they didn't use a lowercase k, or they didn't underline, or whatever, okay? Help them with that. That's the idea. And if you are brave enough to come up here and do it for the class, I might be nice enough to give you a little bit of extra credit on your grade.
Give me on that test.
Listen, here's the look. I don't give extra credit just because I'm giving extra credit. I give extra credit because it has some value to what we're doing about learning chemistry. Now, here's the reason why. When you put yourself under the pressure of coming up here in front of the class and doing it, you are giving yourself a semblance of the kind of pressure you're going to be under when you do a test or a quiz.
Yeah.
Okay? So you are preparing for success by putting yourself under that pressure. Okay? And we're trying to make it easy on you by hopefully it's lighthearted like it was today. That's good. All right? So I think that sort of thing is a good thing, and it's worth a little bit of extra credit. But the extra credit that I give you is a little bit, but it builds up. So you get a little bit now, a little bit later, and pretty soon you start looking at some real points. Yes? All right. Any questions about that?
No.
Yeah, can we do one more?
One more?
Yeah.
I'll do it again.
He just wants to do extra credit.
I need it.
Last one we're going to do. Okay?
Can I do
No,
it
you
again?
can't just go up there. What are you doing?
No, only one a day. You know, we'll try to give somebody else a chance.
I get Trey. I started Trey.
Yeah.
I say Morgan. I do it. I'll give you some.
All right, there you go. Solve the problem. All right, we have another guest student solving this problem. Oh, I'm sorry. Not a guest student, a guest teacher. Okay. Sit down. Someone's done.
I got this. Yes,
We
what
don't
is my
say
name?
their names on camera.
Okay.
If I'm recording it, I don't want to. I mean, first names is not really a problem. Listen, first names is not really a problem, but I don't identify students by name on videos that I publish on YouTube.
Oh man, I could be like a YouTube famous.
Publish me.
I got the
If it's put out in a way that the public can get to it, it's published. If technically speaking, if I'm presenting it to you, I'm publishing it, okay? Because that's publishing to a small audience, but it's still publishing.
Do you like post the videos like right after this class?
Are you talking to me?
Usually sometime
I
later
try.
in the day. Last night was sometime in the evening before I got it done. You need to, that coat cannot be out in this class. Okay?
She knows what she's doing. Same as
Hey, y'all don't give me time.
You know what?
Yeah, I'm proud of you.
It doesn't really matter how long it takes you to get there, as long as you get there.
Yeah.
Doesn't matter.
Y'all remember the story of the tortoise and the hare?
Yeah,
I'm more like
Where?
That's an 8.
Oh, here. Better?
what actually did this?
You thought it was a headless snowman?
I got that.
Boy, she was so sure she threw down that pen, didn't she?
I
got that wrong.
All right. Now, I hope as you do these things, you get better at it, and you find out where your errors are. Again, look, everybody fails. Okay? Everybody fails. You need to fail. But what you need to do is learn from failure so that when you get to the test, you won't. That make sense? All right. By failure, we sort out what the errors are that you're making. All right. Now let me. I'll get to the question. If I'll get everybody's attention, calm down, please. Let me give you a homework problem, and then we're going to take out last night's homework and go over that. Okay?
Tyler sent the question.
Wait, we have homework?
I thought it said lost.
I forgot now.
Well, that's a good question. The question is, I thought the question said loss, and you're right. Now, it did lose this amount of energy. What I did not say was what was the change in enthalpy. In which case, this would have to be a negative number, and that would be a negative number. Okay? If I ask, what is the change of energy in the system if? Then if it's an exothermic reaction, the system is losing energy, this number would be negative. And then this number would be negative. Okay? Listen, please. Listen, please. Listen, please. Okay. If the question states, what is the change in energy in the system? That's this symbol right here. If I'm asking about the change in the energy of the system, or I'm asking about the change in enthalpy, then the amount for an exothermic reaction is always negative. Okay? In which case, then, you would write this as a negative number, and your answer is going to be negative. Does that make sense?
Enthalpy will be negative.
Okay? All right, that's your homework problem.
Hold on, wait.
Okay, so the first of last night's homework problems. Everybody's exchanged their paper?
Yeah.
Okay. First of last night's homework problems was to draw an activation energy diagram that includes a catalyst pathway for an endothermic reaction, and it says to label everything. So we need a graph. So we need X and Y axes, and that would look like this. Okay? And so, now you remember you're supposed to have a title for every graph. I won't count off if you don't today. I also said yesterday this is not a true independent and dependent variable relationship, so you don't have to write the title in the independent-dependent variable relationship form that I want you to do for labs. Okay? In this case, you're just going to say reaction energy diagram, endothermic reaction with catalyst or something. Okay? Reaction energy diagram. We're not going to count off for not having the right title, but for today anyway. I might in the future, because I'm teaching it to you now again, but just to be, for now we won't count off for it. And for an endothermic reaction. All right.
That means it's absorbing it, right?
Wait, is that supposed to be?
Yeah, it's absorbing energy.
Wait, we're not counting. I'm done.
All right, now, let's see. If it's endothermic, it must be taking in energy. The energy is coming from the surroundings. You and I are in the surroundings. The chemicals are absorbing the energy, okay? Now, so we're going to start high, and we're going to end low, okay? This is endothermic. Now, oh, you're right. This is exothermic. I'm sorry. I apologize. You're right. Starts low, ends high. Man, keep me straight. There you go. All right. It does start low and end high. Because that's how you absorb energy. Hopefully I would have figured that out after a while. Gracious, help me. All right. Maybe, we'll see. All right. Start low and end high. Okay? Now, this is the progress of the reaction down here. And I don't care whether you labeled it progress of the reaction or reactants and then products. Either one is fine as long as you have one or the other. I'm going to put both down here, okay? But you have to have a label on the the x-axis. Progress of reaction. Or you could have put reactants going to products. Either one's okay. Okay? You must label the y-axis as being increasing in either heat or energy or both. I'm going to put heat energy for right now. Technically, it should be just energy, but most of the time we think about it as being heat. Okay? Now then, there has to be an activation energy, so you've got to have a peak somewhere above both of these lines. All right? The energy has to go higher in order to get the molecules that are reacting, molecules or ions or whatever it is, to bang into each other with enough force and the right orientation for there to be an actual reaction. Okay? And so for that, you've got to have activation energy, so you've got to be up the hill here somewhere. All right? Now, we need to identify what the change in enthalpy is. Okay? So I'm going to put a little dotted line here over to there and show the enthalpy in the system, or actually enthalpy is in the system, delta H. You could say that's enthalpy if you wanted to. And that's a positive number, right? Now look, listen, we're not going to count off if they don't put positive, but I want you to put positive on there if they don't have it. Okay? They can have either delta H or enthalpy. Either one is fine. But if they don't have delta H and enthalpy, I want you to tell them it's, fill in what they don't have. Does that make sense? Now this one right here, that's the activation energy. That has to be labeled as activation energy. Okay? Now, drum roll. Here is the catalyst pathway. All we're doing is shaving off the top of the activation energy hill. Okay? Okay? So this is the catalyst here. You did? Uh-oh. All right? Now that's what you need for full credit. Okay? So, let's count off the points then, okay? We got a point for heat energy over here. We got a point for either progressive reaction or reactants to products that down here. So that's 2. You got to start low and end high. That's 3 and 4. You got the activation energy hill. That's 5. We're going to show the change in enthalpy. That's 6. And you need to label it in one of these, either this or this. That would be 7, right? Activation energy arrow, showing that's what the activation energy is from the starting energy to the ending energy, to the top of the hill here. What does that be? How about count? 8. Then the label activation energy is 9. The curve for the catalyst is 10. and the word catalyst to label it somewhere, either pointing an arrow to it or on top of it or something. What it come out to be, 9? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right, 11 points. We're not counting 4 against that activated complex. That's good. It's good they did. All right. So 11 points total. But let's make that clear, okay, because she made a good point. All right. While I'm not giving points for it, it would be a good idea for them to have activated complex. Activated complex here. Now, since we're talking about this, let's be careful. Listen. Activated complex almost belongs with reactants and products because it's part of the chemical system itself. It's part of the chemicals. It's not part of the actual reaction energy diagram. Okay? What we're saying here is that when reactants and products get together, when they band together at the correct orientation and speed, we get a temporary complex of these atoms, this crunching together, this thing that won't stay together but just a tiny fraction of a second, called the activated complex. It's not part of the energy hill. It's not part of the curve. It's actually part of this stuff down here, more than up there. But that's where it happens. When you reach the top of the hill, you have an activated complex, okay? All right, 11 points for that. Everybody got it? All right, so that's the homework. I know. I'm gonna give you the. We're gonna do the other one here. All right, I haven't forgot about it. Gibbs free energy now. All right, so the second problem asks you to use the Gibbs free energy equation to predict whether the creating of ammonia from nitrogen and hydrogen in the air is spontaneous and under what conditions. So let's write out. I'm gonna write out the equation on my paper here. Not really. They don't need it if they already wrote it down. When they wrote it down, it's okay. All right. So we got the terms are delta G equals delta H minus T times delta S. Okay. So looking at this problem, does it look like to you that we're increasing or decreasing entropy? Oh, I haven't balanced the whole equation. I gotta have 3 here. Okay. Now, are we decreasing entropy or increasing entropy? Entropy is disorder. I'm seeing 1 plus 3 or 4 particles on this side and 2 on that side. I'm decreasing entropy. Okay, so that's a negative term there. All right. Well, I have no indication of any change of physical state. They're all gases. I don't have any indication that this is hotter than that. All I know is that there are 1, 2, 3, 4 particles on this side and 2 on this side. If I'm decreasing the number of particles, I'm decreasing the disorder. That's a negative term. Temperature is always positive. Am I increasing the heat energy in the system? Actually, I don't know that you know that. Do you know that? Okay, so I'm going to put a question mark there. All right? Okay. Now then, delta H, let's see. Basically you guys wouldn't know right now, so you have to have an argument based on the fact that you don't know. All right? So, since we're subtracting this term, and a plus term times a minus term gives me together a minus term. So we're subtracting a minus term, which means that overall, this is a plus, right? Okay. So now we have to have an argument that explains what would happen when we have all this is plus. In order for this reaction to occur, delta H has to be negative. Okay? So, this reaction will only occur if delta H could also say change in enthalpy. Or you could say the energy stored in the system because all these mean the same thing. You could say goes down or decreases. I'm going to use the word decreases, okay? Alright? Does that make sense? Now, in order to get full credit for this, they have to have some justification, and the evidence is part of the justification, okay? And the explanation. So you claim, evidence, reasoning. Your reasoning has to be sound and match the what you have over here, okay? Based on what I gave you, it doesn't seem to me that there's anything else but this. All right. So let's say that this claim here is going to be worth 5 points, and the justification over here is going to be worth 5 points. So this whole thing is worth 10. All right.